Okay, these were the chapter review questions at the end of the chapter, and I thought it might be nice to go over those. You're supposed to give an example of a scientifically accurate statement in the Bible, list 6 characteristics that would have to be true of either God or random chance. So these may be test questions for those that are taking this class for credit. Give an example of a characteristic of the God of the Bible that would not be true of random chance. Some followers of Eastern religions, such as Hinduism, believe that the whole universe is what? Part of a dream being dreamed by one of the highest gods. And the belief that you are all alone and you're making up the rest of the universe to keep from going insane is not an uncommon thought. It even has a name. And you're supposed to identify something you know through your senses, something you know only through authority that you cannot test for yourself. Come on. Oh, come on, don't tell me my pointer quit working. There it is, okay. You're supposed to identify something that humans say they know only through logic, but no one can ever actually test it. Number 9, what would be the only way we could have absolute certainty in our knowledge? Number 10, what are the 3 types of knowledge used in scientific investigation? Science occurs when, can be tested because it can be what, requires one or more whats. History occurred in the blank, cannot be blank, but we believe it because we have blank accounts. If evolution, that is apes to humans, occurred, it was in the past, if it occurred. It cannot be what? We have no what accounts. It's nothing more than a what system. And then some of the so-called historical sciences like historical geology and archaeology are not considered operational, that is experimental science, because they deal with events that cannot be repeated so as to be what? Well, if you're watching this as a recording, I would recommend that you get the answers to those and pause, next, pause, next, pause, next. But let's go through them. An example of a scientifically accurate statement in the Bible. There's a bunch. It talks, for instance, about the hydrologic cycle, that the waters make circuits and the sea is never filled. It talks about currents in the ocean, many, many other things. Look back through the chapter and you'll see those things. 6 characteristics that have to be true of either God or random chance. If you're an atheist, you still need to believe in something you can't see, invisible, something that's not part of nature, supernatural. How long has either God or random chance been here? Eternal. Where have they been? Everywhere, omnipresent. And what is either God or random chance responsible for? Everything. That is all powerful, omnipotent. And who made God? Nobody. Who made random chance? Nobody. Self-existent. So you have to believe in something or someone that has all those 6 characteristics. Now here's an example of a characteristic of the God of the Bible that would not be true of random chance. Random chance doesn't care about you. The God of the Bible is loving, he's wise, he's all-knowing. In fact, he's so loving, he sent his son to die for you for your sins. You can't say that about random chance. Some people that follow Eastern religions, such as Hinduism, believe the whole universe is nothing but an illusion. It's part of a dream being dreamed by one of the highest gods, like Vishnu. A lot of people say it's Vishnu. And so if Vishnu ever wakes up, well, sorry, existence ends, and then he'll redream a whole new universe. The belief that you're all alone, you're making up the rest of the universe, it's called solipsism. That's been around for a long time. And I think intelligent people tend to ask that more. So this is what René Descartes was struggling with. And he came up with a conclusion, well, I think, therefore I am. And then he realized, okay, the rest of the universe could either be an illusion created by God on purpose, or it could be an illusion created by random chance, or it could be real. Well, if you believe there's a God, why would he make sure you're always deceived about everything at all times? You're not that important, I'm sorry. And random chance wouldn't deliberately make a decision to do anything. Okay, there's many things you know through your senses. You know colors, sounds, smells, tastes, and so forth. Something you know only through authority that you cannot test for yourself. Well, when were you born? How do you know? Your mama told you. How do you know she's your mama? there are many things that happen in the past, and then things like distances to the stars. I can't personally measure those things, so I would have to say that I know those based on some authority that wrote a book that I read. Then, something that humans say they know only through logic, but there's no way any human being can test it. Well, how old is the Earth? 4.56 billion years. How do you know that? Was anybody there? Did anybody write that down? No, they just figured it out through logic. What if the logic is wrong? Well, then, the age of the Earth is wrong. Where did human beings come from? If somebody says, no, I don't believe that there was a God that created us, then they would have to logically figure out, okay, this is where we might have come from. And later on, we should get into the fossil record of so-called ape men, humans and apes, and the origin of life. We will probably get to that next week, or possibly the following week. Some things, the only way that we could have absolute certainty. Can you trust your senses 100%? No. If you go to a court case, you're going to have two witnesses that saw a robbery take place. One of them says the robber was about 6'2" and had dark hair. Another one said, no, about 5'11", had light hair. Same person. Your senses aren't perfectly reliable. Is your logic perfectly reliable? No. You could make mistakes with logic. The only way you could be absolutely certain of absolute truth is if you had an absolute authority, a perfectly reliable eyewitness. Well, there is no such thing among human beings, but if there's a perfectly reliable God, that's going to be the source of absolute knowledge. And the Bible claims to be the record of a perfectly reliable eyewitness, God. I take the Bible for what it is, and there's a different course that I teach, or you could take Bible apologetics courses on how you know the Bible really is the Word of God and not just the invention of humans, but that's not what this course is about. Remember, this is primarily a science course. Three types of knowledge that are used in scientific investigation are, of course, you're going to use your senses. When you do your experiment, you watch, see, hear, feel, smell, taste, record something, watch it later. And then if you don't do research into what other people have done, you're really dumb and you're wasting your time. It's an important thing in science that you appeal to authority. And my camera just quit recording. Why? Okay. This week it looks like my camera wants to give me trouble. I even bought a new microphone, so I won't have trouble with that. Okay, so the three types of knowledge that you use in science, of course, your senses, authority, but also logic, because you try to figure out what's going on here, what's the cause and effect. Science occurs in the present, so you can repeat it and test it. Present, repeated, and you have to have at least one person observe it. If nobody sees it, well, it's like if a tree falls in a forest and there's no one there to hear it, is there sound? Well, there's sound, yeah, but nobody observed it. And of course, you guys have probably heard this. If a man speaks in a forest and there's no woman there to hear it, is he still wrong? That's not true, is it? Okay, so history is something that occurred in the past. You cannot repeat it, but we believe it because we have a number of eyewitness accounts. If evolution occurred, for instance, apes to humans, if it occurred, it would have been in the past. And we can't repeat it. Nobody's ever been able to make an ape gradually evolve into a human, and we have no eyewitness accounts. In fact, it's not possible to have eyewitness accounts because they would have been apes, and apes can't write. So evolution is nothing more than a belief system. So-called historical geology, which is telling us this happened millions and millions and millions of years ago, that and archaeology are not operational science because they deal with events that cannot be repeated, so they can't be tested. Maybe they're true, but there's no way to test them. Okay, moving to the next one. I'm going over the review questions from the first few weeks because I realized, I never went over those with you guys. So those that are watching the recording, give me a second, I've got to switch. Okay, in chapter 2, we talked about measurement and measuring systems in science. Science requires measurement for what reason? What's the difference between qualitative and quantitative? What was the basis of measurement centuries in earlier centuries? What object was used as a basis for measuring length in the original metric system as defined by the French? The metric system identifies fractions and multiples by using what? The original definition of a gram was the mass of 1 cubic centimeter of something. Acceleration is a change of something over time. The Fahrenheit temperature scale was defined, something was defined as the temperature at which water would freeze no matter how much of a substance was dissolved in it. On the Celsius scale, it was a little different. 0 was defined as the temperature at which what kind of water would freeze. The name of the absolute temperature scale used by chemists is what? And then how much is 10 to the 0? How much is anything to the 0 power? It's a little mathematical thing having to do with exponents. Anything to the 0 power except for 0. That's going to be 0. Scientific notation you use to make it easy to write very what numbers. Number 12 million in scientific notations. Okay, why do we want to get numbers? Why do we do measurements? Because we want to have repeatable and reliable results. If you just get something one time, who knows if that's right. But when you measure it and you get the same measurement over and over, you can be a lot more confident. For instance, there was a report some years back of somebody that said they achieved nuclear fusion at room temperature, but nobody else was able to duplicate it. So that's not considered reliable. The difference between qualitative and quantitative data: qualitative says, okay, it's hot, it's big, it's kind of reddish. That's some property without numbers attached. Quantitative has numbers attached. It's 14 centimeters long, it's 82.5 kilograms, the wavelength of light coming off of it is 382 nanometers. It's got numbers attached. It's better whenever possible to attach numbers to your measurements. And what was often the basis of measurement systems in centuries past? Well, of course, King Henry I used the royal foot as the basis of measurement. So that was the foot, King Henry I's foot. So many times the body parts of kings, rulers, and so forth, from the tip of the royal nose to the royal fingertip, was 3 times the length of the foot. Okay, that was the yard. The French said, with their French accent, of course, we can do better than those English pigs. They decided, instead of using people's body parts, which are going to vary from one person to another, they would use the one object that's the same for everybody on the planet, which is the planet. The distance from the North Pole, well, the circumference of the Earth had been calculated several thousand years earlier by Eratosthenes to within about 50 miles. So by then it was pretty well known, and the French said, let's take the distance from the North Pole to the equator, through the greatest city on earth, of course, Paris, and that was going to be the standard of measurement. It was about, I can't get this on the camera. It was slightly longer than a yard. I said, that's convenient. And then in order to identify fractions of that or multiples of that, they do prefixes. You start with a meter, you can do, getting larger, you can do kilometers or kilometers. Getting smaller, you can do centimeters, decimeters, millimeters, micrometers, nanometers, picometers, all of these things. And it's the same basic unit, but that tells you what fraction of the unit it is. The original definition of a gram. They also wanted something that was going to be the same for everybody on the planet, which would be pure water. You just take some H2O, make a little box, 1 centimeter long, wide, and high, 1 cubic centimeter, put water in it. What's that mass? 1 gram. Or if you take a box that's a decimeter, about that big, that big, that big, fill it with water, that's 1 kilogram. So that's also been called the liter nowadays. When you go to the store and you buy your 2-liter drink, you just think of that original box that the French guys made to fill with water. Acceleration is a change of velocity. which can be either change of speed or direction or both. On the Fahrenheit temperature scale, you might wonder, why is 32 not the freezing point of water? Well, Fahrenheit realized that when he dissolved things in water, it was going to lower the freezing point, and eventually he would get down to the point where it was going to freeze no matter what you put in it. He said that's 0. Well, if you take pure water, it worked out to 32 degrees. The human body was used for an approximation of 100 degrees, so it worked out to 212 degrees for the boiling point of water. On the Celsius scale, Mr. Celsius said, oh, forget this stuff about dissolving things. Let's just do pure water. So when pure water froze, that was defined as his 0. It's the same as 32 on the Fahrenheit scale. So if you travel back and forth between the United States and another country, you leave the United States when it's one day I got on a plane and it was 93 degrees. And I got to a foreign country and it was about 4 degrees. But I didn't freeze to death. It's because it was a switch from the Fahrenheit scale to the Celsius scale. Actually, it was pretty cold. I was south of the equator, and so 4 degrees is about 39 degrees. So flip the 93 to 39. And the name of the temperature scale that chemists use, which doesn't care about water, is kelvins. When you're dealing with gases, so what? Water freezes. I don't care. You're trying to figure out things about gases that can be well below 0 on the Celsius scale. And 10 to the 0 power, anything to the 0 power is 1, with the exception of 0 to the 0 power is 0. It has to do with how exponents are defined to work out. Scientific notation is used to make it easy to write very large or very small numbers. And one example, come back here, you. One example, the number 12 million in scientific notation is 1.2 times 10 to the 7th power. Okay, so I need to walk over to the computer and get the next one. So remember, those of you that are watching online, that all of these things are on the Liberty Ministry College, not Liberty, Legacy Ministry College Moodle. They're also available on my website, which is creationorevolution.org. Next question, why is peer review important in science? And why is it important to have only one independent variable in an experiment? What's the purpose of having a control group? What's the purpose of a scientific law? What's the purpose of a scientific theory? Why is it incorrect to say evolution is only a theory? Since we cannot directly test things that are too big, too small, too slow, too fast, past, future, and so forth, what do we do so we can still study them? Empirical means what? The difference between empirical or operational science versus historical science. And an example of an empirical part of biology, and something that is usually considered part of biology that really is not. It should be called historical biology. I'm substitute teaching in a biology class right now, and they needed somebody long term. And I told the department chairperson that there are certain things in the books that are wrong, and I object to teaching those. She said, well, we don't get that till the end of the semester anyway. But you'll see what that is. Uniformitarianism, what is that? And how does 2 Peter chapter 3, verses 3 through 6 tell us that uniformitarianism is wrong? That's a hard word to say repeatedly. Uniformitarianism, uniformitarianism. Okay, so why is peer review important? Well, as I said a few minutes ago, somebody claimed they had made nuclear fusion occur at room temperature. Okay, fine, let's see that. Let's see somebody else do that. Peers said, you got to be kidding. No, there's no support for that. Peer review is important to avoid mistakes, to reduce bias, to make sure proper procedures are followed, things like that. And so I read recently, somebody was complaining about peer review. They said, those evolutionists are just reinforcing each other. Yeah, but it's not just evolution. It's physics, chemistry, biology, actual biology. Peer review is important. Try to help make sure that you didn't overlook something. Why is it important to have only one independent variable in an experiment? So you can be confident that the thing you thought was the independent variable that you changed on purpose really did produce a change in the other thing. You're looking for cause and effect. So if you have 5 different things that are going to change, you can't tell which one of them caused the effect. Could be 2 or 3 or 4 things. And that's also the purpose of having a control group in an experiment, to be sure you're not overlooking something. If you're doing an experiment and you're trying to see what's the result of changing the brand of fertilizer on plants, well, you have a control group that you don't change the brand of fertilizer, and then you have the plants you're experimenting on where you do change it. But if they all die, including the control group, that would let you know, oh, there must be some other factor that I didn't notice, didn't know what was going on. The purpose of a scientific law, a law doesn't make anything happen. A law says this is what happens. So the law of gravity doesn't make anything fall. It just says the force of gravitational attraction between 2 objects is given by this formula. Why does gravity exist? Well, that's what you need a theory for. The purpose of a theory is to try to explain why the thing happens that the law describes. So you're normally going to have more theories than you do laws. There's one law of gravity, but there are at least 3 different explanations people have come up with for why they think gravity exists in the first place. Why is it incorrect to say evolution is only a theory? In ordinary conversation, a lot of times people will say, well, my theory is something, meaning my guess is whatever it is. No, in science, a theory has got a very precise meaning. It's an idea, a proposed explanation that can be tested and has been tested over and over and over again and has never failed a test. But there's always, it's always possible that it could be falsified. So evolution is not a theory. It can't be tested. Instead, you call it a model. In fact, there's not just one model. There's multiple models of evolution. One says it was a slow, steady, gradual process. Another says it occurred in sudden jumps. So since we cannot directly test phenomena that are too big, too small, too slow, too fast, past, future, so and so forth, you can still study things by using models. We do that with the atom. We don't know what an electron is. And if I ask you, tell me exactly what an electron is, people will normally give an explanation. Oh, it's a negative particle, blah, 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 blah. No, we don't know what it is. If somebody ever tells me exactly what it is, I will steal your idea and send it to the Nobel Prize Committee. We know how it behaves, but we don't know what it is. So we use a model. Sometimes we treat it as if it's a little particle, sometimes as if it's a wave. We really don't know for sure. Empirical means determined by experimentation. The difference between empirical and historical science, empirical things can be tested. So when you talk about the theory of evolution, it can't be tested. It's not empirical science. It's so-called historical science. People believe it happened, but they can't test it. The idea that Australopithecus evolved into Homo erectus, which later on evolved into Homo neanderthalensis, which evolved into Homo sapiens. How are you going to test that? That's something that if it happened, it was in the past, and there's no way we could put it in a test tube and repeat it. An example of an empirical part of biology, well, you can study how things grow, how they reproduce, how they interact with their environment, respiration, excretion of wastes. Those are all things we can observe. Give an example of something usually considered part of biology that's in the biology class that ought to be considered historical biology because it's just a made-up story. That's evolution, the origin of life, the so-called ape men. You can't test those things. It's not part of empirical biology. Uniformitarianism is the basis of the geologic time scale that says the Earth is about 4.56 billion years old. It's the idea that everything on the Earth in its geological processes happens slowly, steadily, gradually, at uniform rates. That's why it's uniformitarianism. And a key to this is there can never have been a worldwide flood, because if there was, that's going to mess up your time scale. That would explain what we think are billions of years in a matter of a year or two. So how does 2 Peter chapter 3, verses 3 through 6 tell us that uniformitarianism is wrong? Well, it says that the scoffers will come in the last days, saying, where's the promise of his coming? Jesus is not literally coming back. Ever since the fathers fell asleep, since the first people died, all things continue as they were from the beginning of the creation. And then for this they willingly are ignorant of. They deliberately ignore the fact that there was a world that was overflowed with water and perished. That's the basis of the geologic timescale, to deny that there was ever a worldwide flood. Okay, next chapter. And then we'll get into new material. Remember, you can get all of these on the Legacy Ministry College Moodle. Where did that word come from? Moodle, anyway. I'll have to Moodle through somehow. Okay, we dealt a little bit with astronomy. Why does the North Star not seem to move like all of the other stars? The other ones seem to swirl around. The North Star doesn't. It's because it's lined up with the North Pole. It's lined up with the Earth's axis. This is actually how you can tell how far north of the equator you are. You can't see the North Star in the southern hemisphere. The Earth is not flat. But there's so many people, they say the most stupid things. The Earth is flat, yeah. If the Earth was flat, cats would have pushed everything off the edge by now. But the North Pole points right at Polaris, that's why it's called that, and you can use the North Star at night. If you're a seafarer out at sea, you have an instrument called a sextant to see how high above the horizon is the North Star. If you're exactly at the North Pole, it's going to be straight over your head. Where we are in New Orleans, it's about 30 degrees up. If you're moving up to higher latitudes, it seems to be higher and higher, and you can tell what latitude you are because of the North Pole, the North Star. And I just answered that question. What does astrology try to predict? Which civilization is believed to have decided that there were 360 degrees in a circle? What's a geocentric model of the solar system? What's a heliocentric model? Why did Aristotle believe there was no such thing as parallax of the stars? What did he believe about the distances to all the stars? Was Copernicus able to back up his ideas about the solar system through experimentation? What did Tycho Brahe, I love that name. People say Tycho, I'll look that up. It's Tycho Brahe. What did he observe that was so shocking to those that believed that the universe was unchanging? How did Kepler formulate his laws of planetary motion? What were some of the shocking things, shocking to scientists and astronomers, that Galileo observed as he looked at the planets with his telescope? What great discovery did Newton make regarding the motion of the planets? When was stellar parallax first observed? A light year is a measurement of what? When were scientists first able to directly measure the distances to Mars and Venus? What did they use to make this observation? Does the Bible say the sun orbits the earth? And what does the earth's tilt have to do with why summer is warmer in the northern hemisphere? Okay, first, as I just said, I gave it away too early. I spilled the beans. The North Star lines up with the Earth's axis, so everything in the sky seems to rotate around it in the northern hemisphere. In the southern hemisphere, there's a constellation called the Southern Cross, and when you look up, there's no South Star, but there's a constellation that looks like a cross, and you go a certain distance down, and that point seems to be still in the sky, and everything swirls around it. So the first time I ever saw the Southern Cross with my own eyes was in Africa. That was so cool. There's a song by Crosby, Stills and Nash. I don't know if anybody is into oldies, but it was called Southern Cross. And it says, when you see the Southern Cross for the first time, you understand now why you came this way. Oh, just to think, how big is this world? How big is this universe? Whew, that's the Southern Cross. Okay, astrology tries to predict, everybody knows this, I hope, the influences of the heavenly bodies on your life. Why are you a cranky person? Because you were born in a sign of whatever. Today I feel really cranky because I'm just so swamped with stuff. So that's not the effects of astrology, that's the effect of having a lot of stuff to do. Which civilization is believed to have decided there were 360 degrees in a circle? The Babylonians, and the Babylonians go all the way back to Babel, which is right after Noah's flood. The Tower of Babel was probably 120, 130 years after Noah's flood. That's when they first decided that there were 360 degrees in a circle. Nobody knows exactly why. There's speculation. They like the number 60 and it's a multiple of 60. Okay, but it takes 365 days to go around the sun. So anyway, if you solve that mystery, let me know. Geocentric model of the solar system, the prefix geo means earth. It's an earth-centered model of the solar system. Heliocentric model, Helios is the Greek god of the sun, Helios, and so a heliocentric model is a sun-centered model. Why did Aristotle believe there was no such thing as parallax of the stars? A few weeks ago we talked about this. If you want to view parallax, then look at an object on the wall and put your thumb up close, close one eye, the other eye alternately, and you'll see your thumb seem to jump back and forth. If you could stretch your arm way out, you'd see there's much less change in the apparent angle. That's called parallax. So Aristotle believed there was no such thing as parallax. If the stars are at different distances, you should be able to see parallax. He said, well, I can't see it. I don't spy with my little eye, stellar parallax. So because he couldn't see it with his unaided eyes, his problem was the telescope wasn't invented for several thousand years after him. When it was, then, oh, look at that. There's parallax between the various stars. So because he couldn't see any parallax, what did Aristotle believe about the distances to all the stars? Well, they must all be the same distance away from the Earth. And Copernicus came along and he said, no, it doesn't work well. Let me do new mathematics. And he said, if the sun is at the center of the solar system, the math is a whole lot easier. The problem was he couldn't demonstrate it because a telescope still had not been invented. So mathematically it was great, but everybody, not everybody, but a lot of people, the majority still believed in a geocentric model of the universe. And then Tycho Brahe, he didn't have a telescope yet, but he sat in his observatory night after night after night, and he had these incredibly precise instruments that let him see to like 1/72,000th of a circle, a change from one night to the next. And while he was watching, he saw a supernova, oh, a new star up there. And then there was a comet moving across the heavens. Previously, people had, like Aristotle had said, the heavens are perfect and unchanging. Aristotle didn't really know who made the heavens. Zeus didn't make it. Zeus came along much later. But at least whoever made it must have liked perfection. But it wasn't perfect. It was changing. And then what did Kepler use to formulate his laws of planetary motion? Number crunching. He didn't have calculus, he didn't have computers, didn't even have graphs. They weren't invented for several centuries after that. He just did number crunching, statistical analysis on an incredible amount of data that he inherited from Tycho Brahe. It began with the orbit of Mars, which was the toughest one Brahe never could figure out. He said, hey, Kepler, do this. And Kepler did it. Took him quite a few years. But when he did, he developed his laws of planetary motion. And when Galileo looked through his telescope, what was some of the things that he saw that were really shocking to other people? The moon is not perfectly round. The sun is not perfectly even, and you don't look directly at the sun. You project it onto some kind of a screen. Otherwise, you go blind pretty quickly. Other planets have moons. Venus went through phases like our moon does, quarter moon, half moon, full moon. There were many comets passing through the solar system. So this was really a shock to people with Aristotle's ideas that said the solar system was perfect. And of course, when Galileo said that the Earth is not the center of the solar system, the sun is the center, y'all remember, I hope, that he was condemned by the Catholic Church, and they said, okay, if you don't back off, buddy, you're going to burn at the stake. He said, okay, okay, okay. And that condemnation was not lifted until 1995. Pretty long time. So the great discovery Newton made about the motion of the planets, people had no idea why they followed the path they did. Some thought that maybe there was some force that was pushing them. Nope, Newton figured out, no, there's a force that's pulling them. They're trying to move forward, but there's a force called gravity that's pulling them toward the sun, and they're just in a continual state of falling around the sun. And the moon is in a continual state of falling around the Earth. And the astronauts in a space capsule, they're in a continuous state of falling around the Earth also. Okay, so people think that all of this stuff is ancient. Well, 1830s is pretty ancient. It's a little older than me, but not that much. But the first time anybody was ever actually able to observe parallax between stars was the 1830s, about 1832. Because even after Lippershey invented the telescope, and Galileo improved it, and Newton improved it, they still weren't powerful enough. When you look at a star out there, the very nearest star of all, as when we observe it in January and we observe it 6 months later in July, you're going to see an incredibly small amount of parallax between that, and you need a really good telescope. Even now, the best telescopes we have, like the James Webb telescope, we can't see parallax for any object more than about 50 light years away. So beyond that, it's all calculations, and we'll probably get to that before the end of this class. Not today. A light year. People think a light year is a year. No, it's a distance. It's how far light travels in a year, which is about 6 trillion miles. The closest star is about 4.25 light years away. And this was something that would be a shock. You know, we figure all this stuff we've known forever and ever and ever. The first time we were ever actually able to directly measure the distance to other planets without doing mathematical calculations was the 1960s, just before Kennedy committed to, okay, let's go to the moon now. That's the first time that we ever had radar that was powerful enough to bounce off Venus and Mars. Previously, yeah, we could bounce it off the moon, but we couldn't tell about the other planets until about 1962 or so. And then Kennedy said, yeah, we're going to go to the moon. Does the Bible say the sun orbits the earth? No, it does not. It says it follows a lengthy circuit through the heavens, which it does, as compared to the cosmic microwave background radiation. Yeah, it's moving through the heavens. And the reason summer is warmer in the northern hemisphere is not because we're closer to the sun. We're actually farther away from the sun. But let's see if this is going to work out. Okay, the projector is my sun, and it's summertime. The axis of the earth is tilted toward the sun, and we get more direct sunlight. Now in the wintertime, the axis is tilted away, and even though we're closer, the sunlight is not as direct in the northern hemisphere. Okay, moving on to some new material then. I don't know a way to get around this, sorry. Anytime now. Okay, last week we got into some physics, and I'm just going to sort of fast forward. Talked about various types of energy. I once had somebody challenge me when I gave a talk to a group of skeptics at the Pontchartrain Astronomy Society. They believe in a Big Bang, And so my topic was on what do we know for sure about the universe? And the answer was not really that much. And actually, they weren't that hostile. I told them I appreciate the fact that they didn't come out with torches and pitchforks, but at the end somebody says, well, what's energy? I said, if I could answer that for you, I would win a Nobel Prize. And the chairman of the physics department, a friend of mine, said, yeah, I'd vote to give it to you. We don't know what energy is, but it's there. Potential energy, kinetic energy, and energy is becoming less and less and less useful all of the time. It gradually is spreading out. We don't know any sort of a force that would have caused energy to clump itself into stars. If there was a big bang, it should have just continued to spread instead of coming together trillions of times to form stars. And why would the atoms come together? We don't know that. Why would chemicals come together instead of energy spreading out into living cells? No, don't know. Oh, I should give you all a quick quiz and say, okay, quick, what are the equations of kinematics? Now, you don't need to know those, just to let you know that they're there. Okay, here's a key thing, Newton's laws. His first law says if there's no net force, no unbalanced force, there's no change. No force, no change. Yes force, yes change. How much change? The equation is F equals ma, force equals mass times acceleration. Come back here, you. Okay, that's one of the most important equations in physics. If you want to know how something is going to change its motion, are you applying an unbalanced force? Right now, there's a force attempting to pull you down to the center of the earth. Why aren't you falling? Because the chair is pushing you up. There's a balancing force. And people misunderstand things like a reaction force. Newton's third law said for every action there's an equal and opposite reaction. That is, for every force there's an equal and opposite force, not necessarily motion. So people think, I've had a number of students ask me if a rocket will fly in space because there's no atmosphere to push on. It's not pushing on the atmosphere. The fuel's pushing on the inside of the engine, and the inside of the engine is pushing on the fuel. So the inside of the engine is closed, the fuel has an opening, so it's going to go that way, which means the engine's going to go that way. It's Newton's third law of motion. So rockets actually fly better in space than they do in the atmosphere. And we're getting close to where we were. When you're in a space capsule, the reason you feel weightless is because right now what you're feeling is not your own weight. What you're feeling is a chair pushing up on you. So when you're out in space, there's nothing pushing up on you. The space capsule is continually falling and you're continually falling. It's not pushing on you. You feel weightless, but if you're in a low Earth orbit, 180 miles or so, you still have around 90% of the weight you have on the Earth's surface. You just don't feel it because nothing's pushing up on you. Is this approximately where we were? No, we had a little more than that. A lot of people have the idea that toilets swirl a different direction in the southern hemisphere. Y'all have heard that, I guess. Okay. Not true. A toilet swirls in the direction it was designed to swirl by the manufacturer. There's an effect. It's not a force. There's an effect called the Coriolis effect. The Earth is turning so that at the equator, you're moving at about 1,040 miles an hour toward the east. But when you're at the North Pole, you're moving at 0 toward the east. So you gradually go from 1,040 to a slower amount. Well, if it's an air current, it moves away from the equator trying to move 1,040 sideways. Meanwhile, the Earth underneath it is not turning as fast. And to an observer on the ground, it looks like the air current is gradually moving that way. No, it's not. It's attempting to go in a straight line. It's just the observer and it's a different frame of reference. And it has nothing to do with toilets anyway. The air masses we're talking about in hurricanes and so forth are hundreds of miles across. Is your toilet hundreds of miles across? No, and the water's not moving away from the equator anyway. It's a very common misconception, though. One time we were at a Christmas party, and I noticed in the bathroom that the toilet swirled the other direction, and I made everybody come in to the bathroom and look at the toilet. That's how I get my jollies. Okay, and then we talked a little bit about waves. So you should go back and watch the recording from last week. There's two main types of waves: mechanical waves, which is where you need particles of matter, and then electromagnetic waves, which go through empty space. So sound is an example of a mechanical wave, a compressional wave. The air molecules coming out of my mouth don't go into your ears. That would be really gross. But what they do is they hit the next air molecules, which hit the next, which hit the next, which hit the next, which hit the next, and they form a wave that goes all the way across to you. Like a slinky, this end holds still, it just moves a little, and the wave goes to the other end, but the particles don't go all the way. Then in the other kind of motion, which is called transverse motion, the energy flows perpendicular to the motion of the particles. So last week we did this where we shook a spring up and down, up and down, up and down. The particles of the spring didn't go very far, but the energy did. It went all the way down. That's called a transverse wave. Electromagnetic radiation, such as radio and light and so forth, can go through what we think is empty space, although there's a question about whether it really is empty space, whether there might be something called a zero-point energy field out in space. But at least there are no moving particles of matter. This is a nice diagram of an electromagnetic wave, so if you put it under your microscope, can you see that? No, it's a mathematical graph showing this is our model of what we think it's like. We can't actually see it. What we see is colors or effects of something. So it's actually a three-dimensional wave, and so we've got one part going like this, another part going like this, but which direction is which? We can't say. This part is up and down, this part is left and right. But really, if you're going to do one of these things on a graph, you need to do all three axes, x, y, and z, of the Cartesian coordinate system. And we talked a little bit about the parts of a wave, from the crest to the trough, the wave height, the wavelength. Frequency times wavelength equals the speed of the wave. And a lot of people, a lot of my students down through the years, for some reason have thought that sound travels faster than light. No. Light travels about 900,000 times faster than sound. The speed of sound in air, of course sound can't go through space. You watch the movies and you hear stuff blowing up out in space. Well, sorry, it's not realistic. But the speed of sound through air is about 333 meters per second, give or take a little, depending on the temperature of the air. The speed of light is about 300 million meters per second. So light is about 900,000 times faster than sound. Okay, and we also talked about the fact that waves can reflect, they can diffract, and they can refract. Refraction is what produces rainbows, and there's a memory aid that science teachers always use, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. So you remember your friend Roy, and he lets you remember the colors of the rainbow. There's more colors than that, of course, but those are the ones that we choose to help students remember. The students sometimes will say, could there be other colors that we don't see? Yeah. We see this much. This is how much there is. It's just a little infinitesimal thing. Every now and then, here's just pure speculation. Every now and then God has opened people's eyes and let them see angels. I think they're just different colors than we are. No, if I'm wrong, does that mean I'm going to hell? Nah. Speculation. Okay, waves can interfere with each other. They can add up. This is constructive interference. They can cancel each other part way or all the way. That's destructive interference. And then you can set up wave patterns, interference patterns. Those are very useful when you're trying to determine things like the behavior of light from distant stars. So you want to see, did this thing shift by a tenth of a nanometer? Too small to measure directly, but you take two beams and you put them to see if there's an interference pattern. Okay, on the electromagnetic spectrum, this is the part that we see. It's measured in nanometers. The frequency is about 10 to the 14th, 10 to the 15th hertz. Our eyes can only detect light from about a wavelength of about 380 to 760 nanometers. There's a whole bunch more out there that we can't see. Certain types of insects and predators seem to be able to see either in the infrared or in the ultraviolet. Well, it's there. We just don't see it. I went to the dentist office today and had a checkup, and they did some x-rays, and a lot of people don't understand. They think x-rays are radioactive. Now, x-rays are just electromagnetic radiation. They're similar to gamma rays, but gamma rays do not turn you into the Incredible Hulk. They turn you into a corpse. Okay, so did we get this far last week? Or further than this? Anyway, okay. Electromagnetic radiation, such as light, radio, microwaves, and so forth, it acts like a particle because it doesn't seem to need any kind of a medium to go through. It's like you throw a baseball. But then it also acts like a wave. It can be diffracted and refracted. So, is light a wave or a particle? Yes. Subatomic particles, such as electrons, they usually act like particles, especially when they're traveling through wires in something like an electric circuit, but they also can be diffracted and refracted. So is an electron a wave or a particle? Yes. That is, it's a wave or a particle, depending what you're doing. How about planets? Is a planet a wave or a particle? Yes. Back in 1924, a French physicist, Henri Becquerel, whose name I didn't put in there, he discovered that all matter, even objects as large as planets and stars, can be described as waves. So is matter a wave or a particle? Yes. This is what the Bible says. Through faith, we understand that the worlds were framed by the Word of God, so that things which are seen were not made of things which do appear. That's Hebrews 11:3. Okay, and then the guy who really got quantum mechanics started, Niels Bohr, I believe he's a Lutheran, a very devout Christian. He won a Nobel Prize for his work. He developed much of the theory of the atom. And Bohr said, compare this to Hebrews 11. He said, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. Everything we call real is made of things that cannot be regarded as real. Through faith, we understand that the worlds were framed by the Word of God, so that things which are seen are not made of things which do appear. He just paraphrased the Bible. And this is a result of studying quantum mechanics and beginning the development of the theory. Okay, so there are certain types of waves that we can perceive differently. You and I may perceive them differently. Sound is a wave. It's a mechanical wave, air molecule going through the atmosphere. They can go through solids or liquids also. Well, sound has a frequency. That's a quantity you can measure with a meter. You read it and it says, okay, it's repeated this frequently, but then I hear a sound and you hear the same sound and I say, man, that's a high-pitched sound. And you say, seems okay to me. Pitch is our perception. Frequency is a measurable quantity. And then the amplitude of sound, right now, I don't know what my amplitude is, but you could take a sound pressure meter and you could measure the intensity of the sound I'm producing. That's a measurable quantity. But Jackie would say, he's too loud. Nancy would say, he's not loud enough, or I would say to Nancy, she's not loud enough. The loudness depends upon the perception of the observer, but the amplitude is a measurable physical quantity, which reminds me, if a tree falls in the forest and there's no one there to hear it, is there sound? Yeah, sure. Because if you define sound as being the vibration of the air molecules in response to a stimulus, of course there's sound. It doesn't matter if you're there or not. But then the Hindu idea says that you create your own reality. So if you're not there, it's not really real. Well, I don't believe that. I think the universe is here whether I am or not. And then another thing, the color of light depends upon its wavelength, which is a measurable quantity. But my favorite color is blue. Somebody else might look at that and say, "Oh, that's ugly." I say, "No, it's beautiful." That's a matter of opinion. And then the intensity of a light is a measurable quantity. You go outside and you say, "Oh, it's too bright." Somebody else says, "What?" They've been outside for a while. So there are some things that are a matter of perception, other things that are definitely measurable quantities. Okay, we did do this last week. I didn't bring my little device back, but there's something called the Doppler effect, which was discovered by a physicist whose name was Doppler. If there is a mechanical wave source or electromagnetic wave source moving toward an observer, or the observer moves toward it, doesn't matter which one is moving, all motion is relative to something, the wave seems to be of a shorter wavelength than the actual wave. So here's the wave source moving that way, or the observer moving that way. The waves are more bunched up there, and this observer hears what seems to be a higher pitch. The actual measurable wavelength or frequency, if you're right there moving with it, is a certain amount, but somebody else hears it differently. So if the two are moving closer together, the wavelength is compressed. If the two are moving apart, the wavelength seems stretched out. We use the Doppler effect with weather radar. You hear this all the time. Doppler radar shows. This tells you not only that there are clouds there, but the clouds are moving away or the clouds are moving toward you. We also use it to determine our motion through the cosmic microwave radiation. This is how we know that the sun is moving through the background radiation field, by analyzing the wavelength. It applies to electromagnetic wavelengths as well as it does to mechanical things. So this is a very exaggerated diagram, but if that's the actual wavelength of a star's light, and that's the normal absorption spectrum, which is where the atoms take in colors and you don't see those colors. It gives you a black line. Now let's suppose that we're moving away from the star is moving away from us. The wavelength is going to seem to be stretched out, and that's greatly exaggerated. So the absorption lines are going to be shifted toward the red end of the spectrum. This one moved to the left, this one moved to the left, this one moved to the left. That's called red shifts. And later on, I think we'll probably get around to talking a little bit about physics out in space. Now this one is also exaggerated the other way. It's from a source moving toward us, and the wavelength seems to be compressed. So in this case, the normal colored lines, you would see these in a laboratory, but the normal colored lines are going to seem to be shifted toward the blue end of the spectrum. And we take that as an indication that we are moving toward the object, or the object is moving toward us. I wish I had a pendulum, but I don't have a pendulum. You can use a pendulum to determine the acceleration of gravity. You have a mass hanging on a string, a bob it's called, and it's hanging on a rope or something that's of low enough mass that it doesn't interfere with the motion. And you can do some really cool calculations with this. You can determine what's the acceleration of gravity. The mathematics have been worked out for centuries. When you pull the thing up here, gravity's trying to pull it down, but the rope won't let it go down, so it's going to swing over that way. Now it's got some inertia, it's not some momentum. It tries to keep going, but gravity said, "No, you don't, come back here." And it goes back and forth in response to gravity. And there's a very simple equation for the amount of time that it takes to do this. If you remember anything about geometry, the circumference of a circle is 2 times what times the radius? Pi, 2 pi r. And also, if you remember from geometry, they talk about the area of a circle, they say pi r squared. That is not true. Pi r not squared. Pi r round. Cornbread r squared. Ha. Anyway, pi r squared. Well, the reason pi is in there is a pendulum is following part of the motion of a circle. That's where the pi came from, not the bakery. So using this equation, the time, or the period, is 2 pi times the square root of the length of the pendulum divided by the acceleration of gravity. You can easily determine the acceleration of gravity. Just get a pendulum of a known length and watch it swing back and forth. Do it a few times so you can be confident that you have the right amount of time. And oh yeah, okay, acceleration of gravity is 9.8 meters per second on Earth. But if you're on another planet, you want to know the acceleration of gravity, bring a pendulum. Same equation, same length, just time it, and you can calculate, okay, the acceleration of gravity on this planet is this much. Each planet has a different acceleration of gravity. When I say acceleration of gravity, I mean you let something go, it's going to start moving and it's going to go faster, 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 except for air resistance. But if there's no air, it's going to accelerate at a very measurable, easily calculated rate. So you can tell that on any planet just using by a pendulum. And then here's one that also shows, I'm sorry, I don't mean to get on my soapbox and gripe about people that say stupid stuff. There's some people that pretend that they're Christians defending the Bible. No, the Bible doesn't say anything like this, but they just want to make Christianity look stupid. There are still people that say that the Earth is stationary and everything is rotating around us. No, that's ridiculous. Any star in space that's past Neptune's orbit, in order to go around us every day, that star would have to be moving faster than the speed of light, just to make that one circle within the edge of our solar system, Neptune. So you get out to Pluto and so forth, they'd have to be going far faster than the speed of light. Anyway, forget it. So there is an idea that was developed by a French guy named Foucault. He said, what if I had a really long pendulum? And I don't know if he's the one that did it, but somebody actually took one to the South Pole and they started the pendulum swinging. It's pretty long. It's like 60 feet, 20 meters or so. It's got a really heavy bob on it that's probably 40, 50, 60 pounds. So it's not going to be interfered with much by air resistance. You start it swinging, if you're at the North or South Pole, then you're going to see the Earth turns under it. In 24 hours, the Earth is going to turn exactly all the way around because the Earth is turning. Not the stars, the Earth is turning. Now, if you go to a museum somewhere, you'll sometimes see these. They don't take exactly 24 hours to go around. The mathematics are pretty complicated because the Earth is turning, but the Earth is not an inertial reference frame. It is accelerating, and it messes things up. But you can see the Earth is definitely doing something. It's moving under it. The rate is not exactly 24 hours because of all of the mathematics involved. There's a pretty cool video which I recommended for the people that are taking this class, and I believe Jared is going to put that on the Moodle. It's called Frames of Reference or Frame of Reference, and it shows a Foucault pendulum at the end of it. Did you watch that yet?
Yeah.
Yeah, it shows a Foucault pendulum. The French guys actually did some pretty good stuff sometimes. Okay, and let's talk about simple and compound machines. What's the definition of energy? Well, we really don't have one. It's the ability to do work. Yeah, but what is work? Work is the amount of energy you put in or took out. So work is energy is work is energy is work. It's like, what's the definition of matter? Anything that has mass and occupied space. Okay, what is mass? It's the amount of matter something contains. So mass is matter is mass is matter. Anyway, energy and work are intimately related. Work is the energy you put into or took out of something. So let's say I have to get a refrigerator up on a loading dock. That's a lot of gravitational potential energy I need to put into that refrigerator, and I'm not strong enough to pick it up. But what I can do is use a simple machine, which allows me to spread out the work over a longer time and a longer distance. There's a certain number of joules of energy I have to put into that refrigerator to get it up there. I'm not strong enough to pick it up, so I put a ramp, and I put it on a hand truck, and I roll it up. And I'm actually probably going to have to do more work because of friction, but still, it's going to be a whole lot easier because I can spread it out instead of trying to go and get it up there in 2 seconds. I can take 3 or 4 minutes to gradually roll it up. So I'm having to put out the same total amount of work, or maybe even a little more, but I can put out a lot less power. Power is how fast you do work. So work is measured in joules, and power is measured in watts. So as I always used to tell my female students, the way to remember the relationship between a joule and a watt, some guy comes along and he wants to give you a joule per second, and you're going to go, what? Okay, so you can use a simple machine to reduce your power. You still have to put out the same total of energy. And I'm talking about a human-powered machine. You know, if you have something with a gasoline engine, electric engine, or whatever. But I just mean for a human to be able to do things, you can use a simple machine. There's 6 basic types, which really ultimately come down to 2 basic types. A lever, and the lever is going to pivot around a fulcrum, which can be at various locations. It can be on the end, it can be in the middle. And depending on what you're trying to do, you may use it to either increase the force you get out or increase the distance you get out. So if my car is stuck in the mud, I take a big old long 2x4 and I put a brick or a rock or something like that, put the end of the 2x4 under the car, and I get about 10 feet away and I pull down on this. I got to move it 10 times as far, but I get 10 times the force. And so then I get the car up enough that I can put stuff under the wheels. So you can use a simple machine to gain force, or if you're playing baseball, you got plenty force in your arms, but you want more distance and speed in that bat. So you multiply the distance. Instead of moving about 1 foot, the bat moves maybe 5 or 6 feet in the same amount of time. You still have to do the same total amount of work, that is energy output, but you gain a mechanical advantage. So a lever, you know, it's not something we would think about, but the ancient guy Archimedes, the Greek guy, hundreds of years before Christ, he invented the lever. He invented the screw. Somebody had to invent it, right? Archimedes, one of the most brilliant men of all times. It's a shame. I don't know if I ever told you guys what happened to Archimedes. He was living in the city of Syracuse, and he was a very valuable advisor to the king, King Hiero. He's the one that discovered the principle about buoyancy, where an object experiences a buoyant force where you put it underwater. And he came up with all sorts of defense mechanisms for the city. So some enemy was surrounding the city and besieging it, and they were going to break through, and the enemy king, he said, hey, don't hurt this guy Archimedes. I want him working for me. Well, some idiot soldier went into where Archimedes was and says, hey, you, come with me. Wait a minute, I'm busy. So this stupid soldier says, you don't know who you're dealing with, and stabs him to death. There's no telling what Archimedes would have accomplished had he lived longer. He invented calculus 2,000 years before Newton and Leibniz. Okay, so the inclined plane, to us it's obvious, but somebody had to invent the concept. So we go from the ground upward onto that loading dock, and it makes it a whole lot easier to do the work. Takes a longer time, but it makes it easier because there's less power. And then something that's a variation of an inclined plane, put 2 of them together coming to a point, we call that a wedge or a knife blade. That's all a knife blade is. It's just a wedge. So you have these 2 things and you put them in a block of wood and beat on it, and it separates the wood. There are also pulleys, and a pulley, if you think about it, is nothing but a lever that it goes all the way around a circle, and you throw a rope over it. So what it lets you do is change the direction that you're applying force. If you need to pick something up, you grab it and you pull. Okay. And of course you're going to go like I do. That's something I picked up from my dad way back whenever he was about to do something difficult. You go, even if I haven't done anything yet, I'm about to get out of a chair, I do that without thinking about it. Well, when you're trying to get something from the first floor to the second floor, you can do one of 2 things. You can carry it up, or you can put a pulley with a rope, and now you use your weight to help you. So you don't have to carry your body up the steps. You use your body weight to help you pull the pulley and get the thing upstairs. So you still have to do the same amount of work on the object you're pulling up, but you don't have to lift your body up. So it's a whole lot easier to use a pulley. And then a wheel and axle is like a pulley with a handle on it. So instead of just letting this go by itself, we crank it. So the wheel and axle is just basically a lever again. And using that kind of thing, you can get so much extra force out. And then there's also a screw. A screw is just another variation of an inclined plane. You wrap it around a center post, and as you turn it, it's going to pull or push whatever you're working with. So since work is equal to force times distance, you can gain more force if you're willing to sacrifice distance, or you can gain more distance if you're willing to sacrifice force. Simple machine doesn't increase the amount of work you get out of it. It just makes it easier by spreading it out over a longer time. You can also put them together into compound machines. For instance, there's something called the block and tackle. That's where you take 2, 3, 4, 5 pulleys and you put them all fastened together, and you throw the rope over the first one, the second one, third one, and of course you have the other thing on the bottom that it's hooked to. And you can get an incredible amount of work out of this, an incredible amount of force out of this. Last year after the hurricane came through, I had a bunch of fence posts that had gotten pushed over, and they had like 100 pounds of concrete on each one, and they were embedded in the ground. So I made myself a nice little block and tackle. It looked like a swing set, and I put about 6 pulleys on it, and on the fence post down at the bottom I had 6 pulleys, so the rope goes around and around and around and around. The number of ropes determines how much magnification of force you get. So if you've got 12 ropes, you get 12 times the force. Of course, you got to pull it 12 times as far, but I didn't care about that. So I was able to just kind of stand there and pull this, 200-300 pound post out of the ground just with my little pulleys. Compound machine. Thank you, Archimedes. Archimedes invented so many things. Where's my head? Did I put my head down some? There it is. Okay, let's talk about electricity a little bit. I'm just touching on some of the general topics in physics right now that I think are practical. So some of you have probably had experience with this. On a dry day, you rub a balloon against your hair, and your hair is going to stand up like that. And also you hold the balloon against a wall, and it's going to stick on it. What's happening there is that electrons are acting like particles. In an atom, they behave like a wave, but in static electricity, they behave like particles. So a balloon is an insulating object. You rub it against a material such as hair or wool or something. Electrons are transferred to the balloon. You got a bunch of electrons on it now. Well, those are automatically going to pull against a positive thing and push against other electrons. So when you bring it toward the wall, this has got electrons on it. The electrons there say, nah, move away, move away. So they move away, and the wall becomes positively charged. It produces a positive charge on the hair on the wall by induction. So this is what lightning is. It's just static electricity. One cloud bumps into another cloud, they get all turned around, and they charge by induction. The electrons move from one cloud to another. When enough of them accumulate, they suddenly jump either from one cloud to another. Cloud-to-cloud lightning is by far the most common. If you go outside on an August evening, a lot of times you'll see up in the clouds, the lightning up there. We used to say the angels were bowling or something like that. But the charge tries to equalize itself. They've been bumping together, too many electrons here, not enough there, and you get a transfer of electrons within the cloud. But then also, sometimes you get enough electrons on a cloud that they got nowhere else to go and they jump to the ground. That's called a lightning strike. Oh, come back here, you. Most commonly, it's cloud-to-cloud lightning, but you can also have cloud-to-ground, or you can even have ground-to-cloud lightning. If there's a cloud that's very deficient of electrons, the ground can channel some electrons upward. And as that happens, the electrons move through the air and they heat it up incredibly fast. And hot air expands. So it expands so fast, what do you hear? The angels are bowling. Thunder. When you're walking across the ground and you've got like rubber shoes on a carpet, you know how you touch a doorknob and you go bzzz? Okay, that's lightning, just on a much smaller scale. Back when I was in college, there was this young lady that came in for a job application. That's back when you had key punchers that had to punch the holes in the cards and you fed them through a card. That shows how old I am. Y'all don't even know about that stuff. But this young lady came in for a job application to be a key puncher. And my friend Doug Sinchak and I saw her, and we thought we knew her. Thought this is one of our friends. She was brand new there, had never been there before. We didn't know that. So we walked across the carpet, dragging our feet. I got one ear, and he got the other ear at the same time. And boy, she came up out of the seat, turned around, and she wanted to kill us. I said, she became a friend later. She got the job, but ooh. Anyway, that's lightning. When you zap the doorknob or somebody's ear or something like that. Another thing that's an example of lightning, when you put your clothes in the dryer and you pull them out, it's miniature lightning strikes. And have you ever heard lightning doesn't strike twice in the same place? That's ridiculous. Lightning frequently strikes in the same place over and over and over again. It takes the easiest path to ground. That's why they put lightning rods into buildings, because they're tall and they furnish an easier path for the electricity to run from the ground to the cloud or the cloud to the ground. And if you didn't have the lightning rods, the building gets damaged. So you know who invented the lightning rod? Same guy that invented the potbelly stove. Oh, he invented like 10 different things. One of the greatest inventors ever, Ben Franklin. He's also the first one that used the term negative to describe electricity. He said that lightning was negative electricity. Fortunately, his experiment failed. You know, he tried to fly a kite. It didn't get struck by lightning. If it had, he would have got killed. But Ben Franklin invented the lightning rod, and there were a lot of people that were upset at him. They said, he's interfering with the balance of nature. God may want to send lightning down and zap people. He shouldn't make these lightning rods. But thankfully, lightning rods are in tall buildings everywhere. So this is the Eiffel Tower. It gets struck by lightning all the time because it's 30-some stories high. How high is it? I've never been there. I don't know, it's somewhere 30-some stories. Pretty high. Okay, speaking of electricity, when you flip a light switch, the light comes on instantly. You know, you could be 300 feet away. You flip the light switch and light comes on over there. Did those electrons go rushing over there to get there so fast? Well, in a direct current circuit, DC, the electrons will get there eventually. They'll go around, but they don't move very fast. They move a few centimeters per inch. So how does the light come on instantly? And in an alternating current circuit, the electrons don't even go over there. They go, and they stay pretty much the same place where they were, like a water wave. If you put a fishing cork out in the lake and it's not a windy day, it's just going to go. That's pretty much what the electrons are doing in an alternating current circuit. It's a weird thing, but the electrons themselves don't carry energy. They don't have to move very far. But they begin to move in response to some source like a battery. They not instantly, but at the speed of light, close to the speed of light, they set up electric and magnetic fields that go all the way through the circuit, and those fields propagate near the speed of light. So you flipped on the switch, the electrons didn't move, but the magnetic and electric fields set up, and they got over there. The speed is not exactly the speed of light, depends upon what it's flowing through, the size of the wires and so forth. But in a DC circuit, eventually the batteries are going to make it all the way around. Eventually the electrons are going to make it all the way around. But you have to have pretty good sized batteries, and the batteries eventually will run down. In an AC circuit, the electrons are just going back and forth, but they create the oscillating electric and magnetic fields that propagate all the way through the wire. And so it's not the electrons carrying the energy, it's the electric and magnetic fields that they produce that transmits the energy. So have you all heard of Thomas Edison, I think? Okay. Thomas Edison was firmly committed to the idea of using direct current, DC. He wanted to have batteries everywhere. and just have the electrons going through the circuit. So he didn't actually invent the light bulb, he invented the long-lasting light bulb. The idea of having a filament inside of a glass tube heat up and give light had been around for a while, quite a few decades, but he said, I'm going to make one that doesn't burn out fast. And he tried and tried and tried and tried and tried. Edison was a tinkerer more than he was a scientist. And he tried all sorts of different things, And finally, it was obvious he wasn't going to succeed. I'm sorry if I'm bursting somebody's bubble. But he said, all right, let me try something else. He hired a physicist, a guy named Francis Upton. In fact, you'll see his name on various things about electricity. And the first thing Upton did was, rather than continue to tinker, he went down to the patent office to find out what's been done before. That's why I tell students you can waste an awful lot of time if you don't do research. Edison wasted a lot of time. So Upton went down and he found out this has been tried, this has been tried, this has been... Why? Nobody tried tungsten. It has one of the highest melting points of any of the metals. So he said, let's try a tungsten filament. It worked, and it lasted a much longer time. Of course, Edison owned the laboratory, so he got the patent on it, and he got the fame, but it was Francis Upton that invented it. Well, Edison was firmly committed to direct current, DC electricity. Nikola Tesla, I believe, was a Serbian immigrant, and this guy, he was so far ahead of his time, we still haven't caught up to him. But Tesla came up with the idea, said, well, no, I think we can get around the problem of batteries. Edison wanted to put batteries every few blocks so you could run people's lights. Tesla said, no, if you make the electricity go back and forth, the electromagnetic fields are going to transmit to the wires, and you just have one central power station powering everything. Well, Edison said, no, that's a stupid idea. Tesla was right. But Edison was kind of vindictive. He had invented the motion picture camera. He did a lot of stuff. I don't want to take anything away from him, but he was vindictive in this area, and he wanted to show people that DC was much better, and this terrible AC stuff that Tesla's pushing for, that's so dangerous. So Edison actually recorded on film a number of animals being electrocuted, and there was an elephant that had crushed its handler at the zoo, and they were going to put the elephant down, so he said, let me do it. And he filmed the electrocution of an elephant to broadcast in movie theaters to show this is how dangerous Tesla's AC stuff is. Well, DC will kill you too. If it's a high voltage DC, your car battery won't. But if you have 100 volts DC or something, yeah, that could electrocute you. So Tesla came up with the idea of alternating current, and he got it started. He actually wasn't the one that made it work properly, but with a direct current, you're going to lose a certain amount of energy in the wires. No, that's not. You're going to lose a certain amount of energy in the wires. But there's an equation that relates to how much power is converted to heat, and it depends upon the voltage and the current and the resistance and all of this. And if you could boost the voltage way, way, way up high, you can lower the current way, way, way down low. You can't do that with DC, but with alternating current, we do. If you look at the power lines out on Power Boulevard, that's probably over 100,000 volts up at the top. But what's coming out in your house is 120 or so. So at the power plant, they produce the electricity, and then they bump it way up high, and you send it across the continent. Alternating current works fantastically well. Tesla even did the calculations where he figured it's better to have it reverse 60 times a second, 60 hertz, and the Europeans, they didn't like that because 60 was not that compatible with the metric system. 50 was a better number. So they did 50 hertz electricity. A lot of places around the world do. And actually it doesn't work as well. Tesla was right. 60 hertz seems to be the ideal amount. But when Tesla invented it, he didn't have the bugs worked out. There was a guy, I think Charles Steinmetz was either Austrian or something like that. There was a guy from Europe that came over on a ship long about the time Tesla had invented this, and his name was Charles Steinmetz. He was a hunchback dwarf, and he was a brilliant engineer. So, from what Chuck Swindoll talked about this, he came to Ellis Island, New York to immigrate, and they looked at him, he's deformed, he's a dwarf. But he said, I have a job lined up. And they said, all right, you can come in. He got a job working with Tesla. He fixed alternating current. He made it work properly. And so he became famous himself. You can go look up Charles Steinmetz. He changed his middle name to Proteus, Charles Proteus Steinmetz. And one of the things that happened with him is he designed the electric system for Henry Ford's manufacturing plant, his automobile manufacturing plant, and got it all working. And one day, this is back before you had airplanes going everywhere, one day Ford got in touch with him. He said, our system is shut down, my engineers can't fix it. So okay, Steinmetz got on a train, went to the factory, puttered around in the office, drew an arrow on a piece of paper, taped it, pointing, and it said, change this part. Okay, so he handed Ford a bill for $10,000. And Ford said, $10,000? You just worked for 10 minutes. So Steinmetz said, let me itemize. 10 minutes work, $10. Knowing what to do, $9,990. And Ford paid the bill. So Steinmetz was a cool guy too. Look him up sometime. Steinmetz. Okay, the way we produce electricity, there are a number of different ways. One of them, of course, is solar panels. This uses a phenomenon called photoelectricity. Solar panels convert the light directly to electricity, and then in a battery, you have a chemical reaction going on, and that converts the chemicals, the electrons into chemicals into electricity. They're DC sources, but that's only a tiny percentage of what we use every day. Every other method produces alternating current by spinning magnets past coils of wire. And we're talking big, serious magnets most of the time. Now, the windmills that you see driving down the highway, those are pretty big. If you look at the size of that thing from the ground, it doesn't look so big. But the whole chamber is like the size of a trailer, on the back of an 18-wheeler. And the blades can be, 50 feet long, 100 feet long? So the whole thing is like 200 feet around. So you get a serious force pushing serious magnets past serious coils of wire. So the turbine has to turn, and this will show you relative size in like an electric power plant of a human being as compared to these things. So you have some force that makes the turbine spin. The turbine's like a big fan. The spinning force can come from water rushing downhill from behind a dam or down a river, something like that. That's hydroelectric. And then you can also put these things by the ocean, and when the tide comes in, that's a lot of water. It'll spin the turbine. When it goes out, it'll spin the turbine again, and you can get electricity out of that. Wind will spin the blades. But the way we generate more, I think this is probably more than hydroelectric, is we have something burn or something furnish a heat source. You can burn oil or coal, and this is going to heat up water. You produce steam, and the steam will turn the blades, and it produces the power. Or we can use the most powerful energy source known to humankind to boil water. Nuclear power. That's what we're doing. The same thing that'll destroy cities, we boil water with. And nuclear power is really the safest. It doesn't harm the environment unless there's some kind of an escape. And I think there's been a grand total of about 3 nuclear accidents. One in the US, one in Japan, one in Chernobyl, which is in Ukraine. And if you've never paid attention to this, in the Bible it says something like a huge star fell down from heaven, and the name of the star was Wormwood. Well, in Ukrainian, that's Chernobyl. Interesting. So, maybe it's something to do with nuclear power. Nuclear waste are going to fall down. So we somehow spin these blades and the magnets go past coils of wire and it produces electricity enough to power the country. So people that say nuclear power is unsafe, well, okay, if you want to go back to the days of horse and buggy and candles and firewood and all of that, okay, get rid of nuclear power. But nuclear power is really the safest thing out there. And in fact, we also even use nuclear power for one other kind of thing. Spacecraft can use nuclear power. If you can move a magnet past a coil of wire, you can get electricity out of it. So somebody came up with an idea. There's a device called a Stirling engine, and it uses heat to expand. The heat is released, it contracts, like a piston moving in and out, in and out, in and out. Somebody came up with an idea where they'll put a small amount of radioactive material on a spacecraft, send it up there, and the heat from the radioactive material makes the piston expand, and then the heat's radiated out into space, it comes back, and it just goes back and forth, and this ought to be able to work for thousands of years. So nuclear power can be used with a Stirling engine to get some pretty good results. Okay, and I love this quote by Einstein. Now, Einstein didn't really believe in the God of the Bible. He believed in, some kind of force. But I love what Einstein said. The most incomprehensible thing about the universe is that it is comprehensible. If it's just the result of random processes, there's no reason we ought to be able to understand it. But yet, we can. The Bible says it is the glory of the Lord to conceal a thing, and the glory of kings, that's us, to search it out. So God gave us all of this brain capacity so we can study things. And the more I study things, the Bible says the heavens declare the glory of God and the firmament showeth his handiwork. Well, you could go into more and more detail and say, wow, 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 cool, amazing, incredible, astonishing. I love seeing what God did. Okay, so that had to do with physics. Now we're going to sort of shift gears a little bit. And I'm on the next chapter, which you have to download from either the Moodle or from my website, creationrevolution.net. Once again, here's my website if you need it. creationrevolution.net, and there's a link that says Creation Science Lessons, U.S. and Overseas. Okay, we've talked a little bit about astronomy, a little bit about physics. We're going to talk a little about chemistry, which will take us into next week, and then we'll start a little bit about biology, and I want to talk about the origin of life and design in nature and how living organisms function. At the school where I'm subbing right now, I told the principal, they need a biology teacher short term, and I'm certified in biology. So I told her, okay, but you have to understand, there's 4 things that the biology books usually say that I think are just absolutely wrong. And she said, yeah, but that doesn't come up till the end of the semester, and I should be gone by then anyway. One of them is the idea that the embryo goes through all the stages of evolutionary development before birth. Another one is the idea that you have leftover organs from an earlier stage of evolution called vestigial organs, like the appendix and the tailbone and so forth. Another is the idea that on the early Earth, when life first began, there was no free oxygen, and that's how the chemical reactions were able to proceed. That's known to be false. There have been discoveries of oxygen in all the layers, all the way down to the bottom, to basement rock. And there's another one, which is the idea that there's mountains of fossil evidence supporting evolution. There's no such thing. The fossils, Darwin even admitted, the fossil record was the most grave and serious objection to his theory, and it remains so. In fact, if anything, it's become more and more of an objection. So I told that to the lady, I have a problem with those 4 things, and I'm not willing to teach those. She said, that's not till the end of the semester, and I should be gone by then anyway. It's an interim position. So let's get into chemistry a little bit. Oh, and next week I'll go over the review questions from this chapter that we just went through. So download the text for chapter 5 from either the Legacy Moodle or from creationrevolution.net. Okay, let me give you a semester-long course in 4 hours. It's going to be kind of hard to do. What's everything made out of? Well, since ancient times people wanted to know. Some were just curious, but others had ulterior motives. The alchemists wanted to turn stuff into gold. You take cheap stuff, junk out of the ground, turn it into gold, and you can become rich. Well, many ancient people, could I ask somebody to give me a refill of water, please? Many ancient people followed the word of Aristotle. Back in his day, he was several centuries before Christ. It was kind of like what people say now: God said it, I believe it, that settles it. Well, Aristotle said it, I believe it, that settles it. Aristotle had an incredible amount of influence because he was a teacher of Alexander the Great. And so when this guy sends his army around and they conquer everybody, you better follow what he says. And he just passed on what Aristotle said. Thank you very much. So Aristotle said that everything on earth is made out of 4 elements: earth, air, fire, and water. Well, what about the things that are not on earth? Up in space, the stars. They're not made of the same stuff. They're made out of a 5th essence, which is called the quintessence. So you may have heard people use the word quintessential. Most people misuse it. It had to do with whatever makes up the stars. So we now know that Aristotle was just flat out wrong. Previously, I've talked about a theory. In science, a theory is a proposed explanation that's been repeatedly tested and never failed a test. If it fails a test and it's just a minor failure, we're probably going to modify it. Aristotle's idea, it was totally wrong. So we threw that out. Nobody believes that everything's made out of earth, air, fire, and water anymore, except maybe the flat earth people. He also said there's no such thing as atoms, which we're going to get to shortly. And in physics, he made a great many incorrect predictions, and they were all disproved later. So his scientific statements were terrible. His logical statements were great. He invented the logic we still use, syllogisms and transitive logic and all of this kind of stuff. So if you ever go to the store and see a bag and it says, contains no chemicals, if you buy that bag, what are you buying? Nothing. Everything's made out of chemicals. Now, if they say contains no artificial chemicals, well, I don't know about that either, because all natural ingredients. There's nothing supernatural in that bag. It's all natural ingredients. So if you go to the store and you see something that says contains no chemicals, no, that's impossible. It would just be an empty bag. As far as we can tell, everything is made out of chemicals. Everything is made out of atoms. This is another one of those things that we call a theory, atomic theory. A theory is a proposed explanation that's never been falsified, but could be. If you can propose a test and it fails that test, you admit you're wrong. Okay. Atomic theory says everything's made out of atoms. So how could you falsify that? Find something that's not made out of atoms. We never have. So it's a very well-supported theory. I have no idea how many tens of thousands of experiments have been done that confirm, as far as we can tell, everything is made out of atoms. So there are now 90 elements known to exist in nature. The only 2 up until atomic number 92 are, I can't remember the names of the 2, technetium and one other one. They've been actually detected in stars. We point our telescopes at stars and analyze the light, and we can see what's up there. So in nature on Earth, though, we've discovered 90 elements, and then in laboratories, people have synthesized another 28. What you do is you take some existing atom that has a certain number of protons and neutrons, and you bombard it with more particles, with more protons and neutrons, like helium atoms or just protons, in a particle accelerator, and if you can get it to stick, you may produce another element. Some of these things have only lasted for a few microseconds, but there were enough records of it that we say, okay, yeah, there is an element number 117. But the ones that occur in nature stop at number 92. So despite what Aristotle taught, Aristotle said there couldn't be any such thing as an atom, because that would imply if here's an atom and here's an atom, look, in between them there's empty space. He said, no, there couldn't be any such thing as empty space because I'm so smart, you got to trust me. So despite what Aristotle taught, everything consists out of atoms that we've been able to see. Of those, the ones that are used in living things, every living thing uses schnapps. So you go to the store, you need your schnapsing list, right? That's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Carbon, hydrogen, nitrogen, and oxygen are the bulk of living things. You got an itty bitty bit of phosphorus in the DNA and the RNA, and you got an itty bitty bit of sulfur in some of the amino acids. But without those sticks, you don't have anything alive. You can have some other compounds, but it is not alive. And then living things use probably several dozen other elements in addition to that. For instance, your bones, they have to have calcium. Not just your bones, though. Another place that you need calcium is in your muscles. In order for your muscles to contract properly, you have to have calcium in them. I saw an episode one time of a TV show called ER, Emergency Room, and in it they had a lab technician brought in because he had spilled some chemicals on himself. And they said, what'd you spill? He said, hydrofluoric acid. They said, how much? He said, about 1 liter. He felt fine. They said, who's your next of kin? Why? You can be dead by tomorrow. Once you get hydrofluoric acid into your bloodstream, it's going to go and it's going to start taking the most active metal it can find, which is calcium, and it can't penetrate the bones, but it goes right through your heart. And your heart has got calcium helping the muscle to contract. So they told the guy, you're going to die. Once it's in your bloodstream, you can't get it out. So you will never, ever, in a basic chemistry lab, fool with hydrofluoric acid. It's deadly stuff. And when you're working in a lab, if you're working with that, you never sit down, and you always wear a lab coat. If you spill it on yourself, you throw that lab coat off, and you're standing up so it doesn't saturate into your pants or whatever. So some of this stuff can be pretty deadly. All right, mammals use calcium, magnesium, manganese, chlorine in your stomach. You have digestive acids. And we even use a little tiny bit of arsenic. Too much of anything will kill you. Too much water will kill you. Besides drowning, you can die of water poisoning. But you have to have even just an itty bitty bit of arsenic. Okay, I want to talk about the two most fundamental principles in all of science. When you take a class in biology, they're normally going to tell you that the overriding principle in all of science is evolution. No, it's not. It's thermodynamics. Biology can only operate within the laws of chemistry. Chemistry can only operate within the laws of physics. The two best demonstrated laws of physics in the whole universe have to do with thermodynamics. Thermo refers to heat, of course, but energy can change back and forth from heat to light to electricity to various other kinds, various other flavors of energy. And so thermodynamics actually refers to any form of energy. The first law of thermodynamics is called the law of conservation of matter and energy. Now, way back when, 150 years ago, there was a guy named Lavoisier, a French guy that, some of those French guys were pretty good. I'm sorry if there's any French people watching this. I love French people. Lavoisier discovered the law of conservation of mass. This had to do with chemical reactions. You don't lose mass when you're finished. You got the same mass you started with. But later it was expanded after Einstein's realization that you can convert matter to energy according to the equation E equals mc squared. The amount of energy is equal to the amount of mass times the speed of light squared. And we've done this in nuclear bombs and in nuclear reactors. Okay, so we've got to take this into account. So it's now expanded. It's the law of conservation of matter and energy. It refers to the quantity of energy. It can be changed back and forth from one form to another, but energy can neither be created nor destroyed by any known process. So you say, where'd energy come from in the first place? Energy and matter. It could either be an unknown physical process, natural process, or it could be an unknown non-natural process. Well, I'm going to go with a non-natural process. I believe God is the creator who made all of this stuff in the first place. So the second law is called the law of entropy. Entropy refers to the quality of energy. It's a measure of the disorganization or randomness or equilibrium of a system. If you have a star compared to the space around it, like our sun and the solar system, there's so much energy concentrated in that star. The space around it contains very little energy. But is more energy flowing into the sun? No, it's flowing out of the sun. We go from greater concentration to lesser concentration. The second law of thermodynamics, the law of entropy, refers to the quality of the energy. It means that energy tends to flow from greater to lesser concentration. That is, things try to move toward equilibrium. If you put a hot and a cold object next to each other, the hot one doesn't get hotter. It loses its heat, it radiates it into the other one, and they tend to reach thermal equilibrium after a while. So there's a great deal of energy in all of the stars. The second law of thermodynamics, which was derived from centuries of observation, says that, energy doesn't come together by itself. It tries to spread out by itself. So we'd have to ask, okay, how did it get in the stars in the first place? We have no natural explanation for it. There's either an unknown natural process following a Big Bang or an unknown non-natural process. As a Christian, I'm going to go with that one. There's a God who is not limited by natural processes, and that's how the energy got into the stars. So even though we really don't have a good definition for energy, it's often described as the ability to do work, to produce change. But in order for work to be accomplished, there has to be a difference in energy level from one place to another. If it's all the same energy level, you can't do any work because you can't transfer any energy. So for instance, a steam engine would work by converting chemical potential energy in some sort of fuel into heat. That heat boils water, gives the water kinetic energy, moves it around, exerts pressure, makes something spin. So when you're finished, there's less energy concentrated in the fuel and some of the energy radiated out into space. This always happens. Energy just keeps radiating into space. So the chemists don't understand why. I took a class one time out at UNO, chemistry for teachers, and the teacher said absolutely every process that ever occurs increases the entropy of the universe, but we don't know why. Well, I do know why, because I read my Bible. It says in Romans 8:20-22, for the creation was subjected to futility, not willingly, but because of him who subjected it in hope, because the creation itself also will be delivered from the bondage of corruption into the glorious liberty of the children of God. For we know that the whole creation groans and labors with birth pangs together until now. The universe is deteriorating. That's entropy right there. When God made the universe at the beginning, it was very good. And of course, energy had to keep spreading out because when Adam and Eve were going to eat the fruit, they had to use it. But it wasn't, we don't know exactly what the conditions were, but it wasn't deterioration like it is now. Somehow, I guess it was perfect recycling or something. So the reason that work can be accomplished right now is that the universe, the earth, the stars, they contain large concentrations of energy, so it's not at equilibrium. But gradually, the energy is spreading out through the radiation from the stars, and eventually the universe is going to reach equilibrium. This is called a heat death. So the energy is gradually moving outward because it's out of equilibrium, but when it reaches equilibrium, no change will be possible. Energy is the ability to produce change. No change will be possible. There'll be no such thing as life. Now the evolutionists will say, well, no, you're wrong, because the second law of thermodynamics has to do with a system that's not subject to outside influences. The heat death, the stars are going to burn out. It's a one-way process. And when I was in China visiting Joe and Betsy, I don't know, 15, 16 years ago, something like that, they were teaching English at Xi'an Petroleum University. And the students there spoke English because they needed to be able to interact with people in the rest of the world. So Joe and Betsy asked the university administration, a communist university, atheistic communist university, if their friend from the U.S., a qualified science teacher, yours truly, could give a lecture on the subject of creation and evolution. They said, sure, no problem. Now, I was teaching in a public school in the United States, and I couldn't talk about creation. But in communist China, in an atheist university, sure, go ahead. So I had about an hour and a half to talk to the students, and they've been taught their whole lives that everything's under control, things are going to get better and better, the government's got this, don't worry about it. And so I said, what can I talk about? Well, they're technical people. I talked about thermodynamics, how the universe eventually is going to die a heat death, given enough time. Of course, before then, all of us will be dead anyway. But one of the students were shocked. One of them said, what can we do about it? I said, absolutely nothing. He said, but what will happen to the universe? I said, it'll die. And I said, that is unless whoever started the stars in the first place and put the energy in the stars in the first place fixes it. And the Bible says he will. So it was wonderful to be able to use thermodynamics to plant some seeds in these young people. But then the evolutionists will sometimes say, yeah, but the reason this doesn't apply is because the Earth is not an isolated system. It's not a closed system. Energy can get in, no problem. So entropy can decrease. Well, you can cause a decrease of entropy, decrease of disorganization, increase of organization under certain circumstances in an open system. The first thing you have to do is have some sort of usable energy coming in. Got to be the right kind of energy. So Ashley just had a little baby. Oh, let's give the baby a lot of energy. Let's set up bombs next to her. No, wrong kind of energy. So you have to have some sort of energy that's in a form that will be useful to that system. And then you have to have some kind of a conversion mechanism to put that energy to use. So let's pile steaks and lobsters around the baby. Well, I'm sorry, her digestive system isn't developed enough that she can convert it into a usable form. You have to have not just the right kind of energy, you have to have a conversion mechanism to put it into a useful form. And suppose you have a newborn baby that has no DNA, and you give the kid all the food you want. Are they going to grow? No, the reason that you got bigger, the reason you grew from a single fertilized cell is because you had DNA. You had pre-existing information that would guide the way the energy would be used in order to put together your body structures. I don't care how much energy you give something, if you don't have pre-existing information, it will not develop into something more complex and more organized. No DNA equals no growth. So people are talking about, well, yeah, the Earth is an open system. Yeah, but at the beginning, supposedly billions of years ago, there wouldn't have been any such thing as DNA. So how could anything have used the energy? And besides that, the energy would have been the wrong kind of energy to begin with. Well, this is where sometimes those that believe in evolution are a little confused. They say, no, things can automatically become more organized just by themselves. Look at ice. If you have liquid water, it'll turn into ice. Crystals are much more organized than the liquid water. What they're misunderstanding is that water always has a bent shape. That's the shape of a water molecule, which was calculated and then it was confirmed by X-ray crystallography. So, yep, that's what it looks like. It's like a Mickey Mouse ear molecule. It's always that shape. But normally the positive end sticking out and the negative end of another water molecule, they're moving too fast so they can't link up. But when you cool them down, we get an attraction between the hydrogen and the oxygen, and it'll form crystals. How much information have we added? None. The information was always there from the very beginning. It's just that we removed enough kinetic energy so that they could slow down and link together. When we removed the kinetic energy, where did it go? It increased the entropy of the universe. So you can have what seems to be a local decrease in entropy, but it's always at a cost. The universe has got to pay for it. Oh, y'all want to memorize this equation? Things can happen only if the Gibbs free energy, their interrelation between all this. Okay. Okay, so let's take a collection of random letters. Write down a bunch of random letters. That's what we got. Okay, well, let's put them in alphabetical order. I'm trying to illustrate the difference between information and order. Order, yeah, not the same as information. Let's rearrange those same letters, put them in alphabetical order, and this is what we got. Wow, look how orderly. Yeah, but does it convey any information, any meaning? Let's rearrange those exact same letters. Is that any difference from the previous two?
Yeah.
Yeah, information is much different than just order. So the idea that, there's more energy coming into the earth and so it could make things more orderly. No, not really. It'll actually make things less orderly, the energy that's coming in, and it's not going to add any information whatsoever. Okay, so back to the idea of an open system. There has to be pre-existing information. Well, yeah, there is in the physical structure of the water molecule. That's why it forms crystals. But then as entropy decreases in my little local area here, things become organized, more organized. It's because the universe is paying for it. There has to be at least a greater increase in entropy elsewhere. There's always a cost. So the idea that if you put in enough energy, you can increase the organization of something is just totally false. Okay, so let's talk a little bit about, well, we've been almost 2 hours. We started shortly after 6. This is probably a real good place to stop for tonight. Next time we're going to continue talking on about chemically. We get an attraction between the hydrogen and the oxygen, and it'll form crystals. How much information have we added? None. The information was always there from the very beginning. It's just that we removed enough kinetic energy so that they could slow down and link together. When we removed the kinetic energy, where did it go? It increased the entropy of the universe.